Thank you.
Thank you so much. I don't know how to feel about that. Being one of America's favorite edutainers, it's good, and I just want to follow a little bit on. I am a college professor, so much so I am at Duke, but I'm also a professor at UW. Most of you don't know that. I have an adjunct position in the aeronautics department. They're constantly trying to woo me out here. You never know when that may or may not happen. But I'm going to talk to you today about a lot of the work that I'm doing in drones and driverless cars. But first, I think it's helpful for you to understand my background because I think it helps set the stage for why is it a person like me did a transition from the military into autonomous systems research. So I was one of the United States Navy's first female fighter pilots, in fact, one of the first female fighter pilots for the United States in general, which means that I'm amazingly fun to take to a bar because I have so many good stories. But why that's really a big marker in my life is because when I did this, and of course it is landing on an aircraft carrier what sets apart all Navy pilots from particularly Air Force pilots. This is what I rely upon when I'm feeling insecure in a room. I just remind myself, we're the CEO of Starbucks. I'm on the World Economics Forum. In fact, I co-chair their artificial intelligence and robotics community. And when I'm with these people, I just remind myself, they've never landed on an aircraft carrier. So this, though, was an amazing transition point in my career because when I did this, and I was flying the A4 first and then the F-18 Hornet, I found out that planes almost always land themselves better by the computer than I ever could, particularly repeatedly. And so that was a little disturbing, but at least when you're landing, you get to put your hands near the controls because occasionally something happens and you need to take control and finish the landing. What was really humiliating was being sent over to the catapult and then being launched off the front of the ship because when you're in an F-18, which is a fly-by-wire aircraft, you have to show everyone, you're pointed this way, you have to turn and you have to show everyone over here, I'm not touching anything. And then you show everyone over here, seriously, not touching anything. And then you hold these handlebars to show everyone you're not touching anything like a 5-year-old. And only when they're sure you're not touching anything, they actually launch you off the front of the ship. And that is because if you touch anything, the plane is flying so close to the stall margin that you could actually introduce pilot-induced oscillations and cause the aircraft to crash. So I was like, I am the best of the best. Certainly that's what Top Gun says. And I'm not allowed to touch anything because the computer, and it always does a better job than the human, particularly on the takeoff. So what does that say about the future? And what does that say about where my career is going? So that, plus a lot of the social upheaval about being one of the first female fighter pilots, led me to get out. I went back to school. I was at University of Virginia, and then went to MIT for 10 years, where then Duke made a power play and treats me like the diva that I am. So now I moved my lab, called the Humans and Autonomy Laboratory, down to Duke. There is a joke in the name. I would presume if you're over 40, most of you get the joke. If you're under 40, you may not get the joke. And you just have to ask somebody over 40 what the joke is. Okay, so I'm going to turn into a little professor here. I'm going to just give you a little bit of a lecture. I call this my secret sauce for how I know what is going to be automated. If you're worried about robots taking your job, how do you know if a robot is coming for your job? So I call this the SRK Taxonomy, skills, rule, knowledge, and expertise. So the way that any human or actually computer agent, any agent at all, reasons through any kind of complex problem is through these levels. The first is skill-based reasoning. In the act of flying, that is a person or a computer learning to keep the plane in balanced flight. And so once you do that, and in fact, it takes humans a couple of years. That's why flight school is so long, so that it becomes very automatic, that when you see the dials and gauges change, you can automatically respond and make the aircraft fly like you want it to. Computers actually do this pretty well. Control aircraft code has become extremely mature. But for a human, once you learn how to keep the plane in balanced flight, then you move to rule-based reasoning. And when you go to rule-based reasoning, you can think of it like procedures. And in fact, there's many procedures. There's a whole book of procedures that you have to go through when you're doing various phases of flight. you can think of this sort of like a cookbook, but if we can think of it like a cookbook, and we know what all the preconditions are, and we have good sensors that tell us what the world around us is, this is actually something that automation does very well. So, you know, you can think of it if then else. If we can think of something as an if then else, which are generally how procedures in aviation are written, then we potentially could automate them, again, with the caveat that sensors are going to work. And we're going to come back to this because this is a huge issue for autonomous vehicles of all sorts. And now you see we're kind of going up this curve, and we're going up this curve because these layers, the skills and the rules, you actually need these higher levels of reasoning as uncertainty in your world grows, and especially when you go to something called knowledge-based reasoning. Knowledge-based reasoning occurs, you need that in your life when there's not a clear rule book, you're not really sure exactly what the rules should be because the world around you isn't what you thought it might be. And then a good example of this is the Miracle on the Hudson when Chesley Sullenberger had to land the US airplane in the Hudson because he took a dual-engine bird strike to the engines and flamed them out. He had to make a guess. There are some rules that you follow when you have a dual-engine flame out, and they had to pull out the book, and he tells a hilarious story that in the olden days, they used to put tabs on the side of the procedure book to help you get to ditching. But in this particular case, US Air had done a cost-cutting move and gotten rid of the tabs. And so he and the copilot have to flip to the back of the book, and it's about this thick, and they're going through the index. D, DA, D, ditching. Okay, turn to page 487. And they lost a lot of time. And in doing so, they had to figure out, they had to run fast mental simulations in their head to figure out what the potential courses of action could be, and then choose the best option. It's not clear that even if had a computer done it, that a computer would have been able to do the same or a better job. So in this case, lots of uncertainty, not sure what's going to happen. The winds in aviation cause a great deal of uncertainty, and you needed a human who has judgment and intuition and lots of experience. And it is that experience that drives people into expert decision making, which is the final, we could say that is what we'd like to, all autonomous systems in theory to achieve is expert-based reasoning. Expert-based reasoning, by the way, most of you know it, is really just rule-based reasoning. Expert-based reasoning in this case is when a system, any system, human or computer, can perform at maximum uncertainty. And we're going to talk a little bit more about how that is not really achievable by today's world, in today's transportation systems, which is what this graph is showing. So understanding the SRKE framework, let's talk about the major forms of transportation, automation, and where we're going in this country. So on the rubric that I just showed you, if we think about rail, aviation, and surface transportation, what we call driving, then we would apply it in this way. So rail, easiest thing to automate, 1 degree of freedom, you're on a track, we know where you are at all time. So, and this is actually a picture of an automated rail service in Australia that automates completely without any humans on board. It's a mining train. How many fully automated trains do we have in America? 0. That is a whole nother set of difficulties, regulatory issues, cultural, business, lobbying, unions. There's a lot of reasons that we don't have automated rail in place, which actually makes us shameful. America is ridiculously behind in automated rail. There are third world countries that have more advanced rail systems than we do. But again, this points to the nature of the regulatory and or corporate culture environment. The next on the list comes as a surprise to most people. Drones are actually not as hard to automate as driverless cars. Why? Well, first of all, when you're in an aircraft or when an aircraft is in the sky, there are not 50 other people of questionable intelligence driving closely, flying closely to you on their cell phones at all times. That being said, the FAAs have a problem with pilots and texting while taxiing, right? So driving is not the only place where your cell phones are causing distraction. So again, because the obstacle density field is not nearly as high, the sensors are far more mature. Planes have been flying by themselves for over 30 years. Right now, in every plane that you fly, every commercial aircraft you fly, the pilot only touches the stick 3 to 7 minutes of the entire flight. They only touch the stick on takeoff. The reason is because the airlines want to save gas. When planes fly themselves, they save a tremendous amount of gas. They reduce the carbon footprint by a measurable amount. And when the planes land themselves, they save the tires. Humans landing on tires, we kind of get on the brakes too hard, too uneven. But when the automation does it, the tires last much longer. And that is why the commercial aviation companies do not want pilots flying these aircraft. They want them as little as possible on the stick. Then that leaves cars, where we need knowledge and expert-based reasoning. And why is it so much harder to do that? It is because for all the possible events, high levels of uncertainty, it's not clear that computers, well, it's not, they cannot right now reason inductively. So most of you, when you were learning how to drive a car, you were told the example, the ball rolls in the street in front of the car. What do? Well, you look for kids, you have this mental imagination, there's one or more kids playing with the ball nearby, and you get your sensors up looking for the other events because you've made a guess about what is causing that ball in the street. Driverless cars, self-driving cars right now simply cannot do that because we do not know how to do inductive reasoning in computer science, and it's not clear that that's in the immediate future. We'll talk a little bit about machine learning in just a second, because I know that some of you want to fight with me about that. So, and let me give you some strengths and limitations, though, of both of these systems, humans versus computers. So this is actually called the Yerkes-Dodson workload curve, and it tells us that there's some moderate level of workload that you perform best at. If you're working too hard, you'll lose attention, you'll drop your workload. It's just difficult to stay engaged. Consequently, if you're bored, and we see this quite a bit in aviation for pilots because it is actually really boring to fly a plane that's flying itself most of the time, you will also lose attention and you'll be easily distracted. So there's another problem too, not just workload. It's something we know of as mode confusion in aviation. Mode confusion is when humans do not understand what the automation is either thinking or doing or why it does what it does. I don't mean to scare you. Flying is still the safest way to travel, but these are the results from a quick study a few years ago about Boeing 737 pilots. And the question was, name 3 ways to turn off the approach control. This is actually the automated service that actually lands the plane itself. So what you'll see is, well, only 3 out of the 20 knew all 3 ways, but even more interesting, 14 named a way that didn't even exist. These are professional pilots with years, all at the minimum was 5,000 flight hours. So anywhere from 5 to 20,000 flight hours, these were pilots who are flying you around, did not know how to actually disengage the automation. These people go through annual check rides every year to make sure that they're staying on top of the game. Well, you know, if that's a problem in highly trained pilots, what are the odds that drivers are going to get it? And so a little over a year ago, I testified in front of the Senate Commerce Committee that driverless cars, the technology was still so immature that, and it was in March of last year, I'm like, someone is going to die with these technologies. And then 6 weeks later, Joshua Brown was in his Tesla, which he placed way too much faith in. He had mode confusion. He did not know the modes of the car, where the failure points were, and a tractor trailer turned in front of him. He had about 10 seconds to see the tractor trailer and engage the brakes. The radar didn't see it, the computer vision cameras didn't see it, and Joshua Brown was killed, right? There is debate within federal agencies. NHTSA says Tesla is off the hook. The National Transportation and Safety Board says it's their fault. But the bottom line is the driver did not engage like Tesla thought he should. But aviation would have predicted this because we know that mode confusion for humans is a serious problem. But I don't want to let AI/computers off the hook. So I work with Toyota Research Institute. They gave me these pictures to show you so that you would understand just how difficult computer perception problems, computer vision problems are for driverless cars. So this is in Boston. One of Toyota's research cars comes up to an intersection, sees this moving van. All of you, this is your inductive reasoning. I did not even have to tell you what it was. Instantly, all of you knew what it was. You wasted no brain power on this. This is what the computer vision cameras saw. The computer vision cameras saw 2 trucks, a bus, a bunch of traffic signs, poles, a giant person, and so, and we can go back real quick. Let's see if I can get it to do it. Yeah, all right, one more time. Fun, fun, fun. Oh, no. So, you know, the good news is that you know, there was a driver in the car, and the car's safety default was to stop, which is good when it didn't understand the scene. But this is a very recent picture of a very advanced computer vision system getting confused. And I can assure you that all driverless car companies are having this problem because it's still difficult for computers to take all the abstract pieces. They're very data-driven, and to extrapolate to the whole. That's deductive reasoning. We look at the whole, and then maybe if we need to, we abstract down to the individual data points. So we're still pretty far from having cars and systems understand. And not only that, this is actually a research effort that just came out. There were a group of researchers, some at Berkeley, some at UW. So hacking, of course, is a big issue. And people think hacking of, like, I'm going to capture the GPS signal, for example, and I'm going to trick the car and going somewhere else. That's one way, and that is a potential way that we're concerned about in driverless cars. But this is actually the new way that we need to be concerned. This is basically tricking the computer vision algorithms. So with these 4 black and white stickers on this stop sign, these researchers were able to trick a computer vision system that you would find on a driverless car into reading that stop sign as a 45-mile-per-hour sign. So this is passive hacking. This is nobody having to get into your system, nobody, you know, having to actively send out any signals, capture any signals. And so, again, this is a research demonstration. It's not coming to a sign near you yet. But if we can do this in a research setting, then we need to be thinking about how are we going to get around this problem, the brittleness of deductive reasoning computer-based systems, and figure out how to maybe join the two together. And so my whole research is about bringing systems together, letting the humans and the computers, the automation, the autonomous systems work together as a team. This is one really great example. We sort of call this, we started this project as the R2-D2 project, where we're going to make a copilot, a robot copilot, sit in the right seat of any aircraft. George Lucas gets really mad when you use R2-D2, so we had to change the name to R2A2. We're so clever, aren't we? And so this is a project with Aurora Flight Sciences, who was recently acquired by Boeing, and so now they're part of the team, the Seattle team. So this robot sits in the right, and the really awesome thing about this robot is you can pick it up and put it in different aircraft. And why do we need a robot in the right seat? Oh, what about jobs? Well, what most of you don't know is there's a huge pilot shortage in the rest of the world, and we actually need a lot more pilots than we have. And by putting a robot that can be transferred between cockpits, you actually double your workforce by taking one person out. And so I would encourage you to go on the internet and look up, Alias is the name of this robot. I know it's a little scary. Alias and Aurora, and you can actually see the robot responding. So the pilot can say, you know, Alias, I'd like to go get a cup of coffee in the back. Will you take control? And the robot arm will come over and grip controls. It can actuate various buttons. And so, but this is meant to be collaborative. It's not necessarily going to replace it. The captain is still there. The captain is still there to apply his inductive reasoning. But the robot is there to take over those boring jobs and let the pilot do what needs to be done and bring his experience and judgment to bear. But one other place I see, particularly in Seattle, that's a whole new cutting edge of where we're going to need to see collaborations and systems. This is the idea of the remote dispatch center of the future. And so we have these for aviation, right? There's a group, there's a big building somewhere where there are dispatchers helping aircraft understand not just air traffic control, but how to move them on the ground. One area that is going to be up and coming that I see big groups of people in Seattle that will be leveraged will be the development of the software to actually have similar types of dispatchers managing fleets of autonomous vehicles. This is an area of driverless cars that really no one's thinking about, but we will not be able to put fleets of these cars on the road until we have remote supervisors managing them, a little bit like an OnStar call center, although OnStar call center plus, where the persons can actually reach in and give active control commands to get the cars unstuck or to maybe resolve problems and contingencies that are absolutely going to arise, especially when it sees the giant person on the side of the truck. Thank you. Oh, and do we have time for questions? I don't see a counter. We have time for one question. Who's the one lucky candidate who wants to ask a question? Okay, there's one way over here. So the question was, have I ever been in an inverted 4G dive with a MiG? Well, I will tell you that I never got to fight against MiGs per se. Have I been inverted in a negative 4G? Absolutely. I have to tell you, when I tell people, it is amazing when it's a man versus machine, when you're flying a fighter like that, to be able to put it into very unusual attitudes, and it's very turbulent. It is so amazing. I don't mean to be a warmonger, but you see me in this way before you, this girl, blonde hair. I think it blows a lot of people's stereotypes away. But the very first time I dropped a 500-pound bomb I had a direct hit on a tank, and I blew it to smithereens. Ladies, I have to tell you, it really does a lot for your self-confidence. Really good, really good. Honestly, if I had a program to empower executive women, it would be, landing planes and carriers and dropping 500-pound bombs on static objects with no people in them. But thank you very much.